In this lesson, we're going to focus our attention on the next concepts related to microprocessor design, and that is understanding interrupts, traps, and exceptions. And so to get started, let's focus our attention on first discussing what exactly do we mean when we say a interrupt. And so let's consider the scenario that we have a student that is asking a teacher a question in class, and the teacher needs a signal in order to determine whether they need to respond to the student or not. So this basically defines that we need some type of mechanism in place to handle possible events that might occur. And so this could represent what we call a discontinuity in the program flow. And so with that in regards, you want to consider that an interrupt is going to be a response by the processor to an event that needs the software's attention. And so this is essentially a mechanism that enables appropriate collaboration to occur between the system hardware and the software. And so the interrupt will provide for an alert or notice for the processor that, that we need to pause at the current iteration in the cycle of our computer activities. And so the benefit of an interrupt is that we want for it to allow for a programmatic suspension of activities. And in this regard, we need to make sure that we can save the current state of the programmatic execution, pause the current status of the function, and have an interrupt handler utilized in order to deal with those events. So let's take into consideration how this factors in. So what we must first be sure to understand is the factors that can affect program execution. And these can be in the form of what we call synchronous events, as well as asynchronous events. And so what we know is synchronous events, they will occur at a well-defined points within our system. And so synchronous events could be cues to make a phone call, or as well as opening a file. Asynchronous events are events that would occur during program execution in an unexpected manner. And so these could be resulted from receiving a phone call, or it could be a user pressing a key on a keyboard unexpectedly. And so the thing to keep in mind with the asynchronous events is that it results in an activity within the system that was not expected. Another example that could be considered an asynchronous event would be retrieving an email notification while you're in the middle of a meeting or some other activity. And so let's consider that depending on the environment or instruction set that is used, that there are different standards that are used to define the various terminologies that are associated with programmatic execution and interrupt events. And so let's define those. Let's for this lesson, let's define what we mean by an interrupt, as well as traps and exceptions. And so we want to consider that a interrupt basically responds to asynchronous events that are produced by specific devices. It can be the I/O devices, and these are events that the processor needs to handle. And so in order to handle it, can result in interruption in the execution of currently executing processes. And so traps are going to be used or defined as representing the synchronous events produced by special instructions. And so this can vary, and typically it could be used to allow someone to have secure access to basic operating system functions. And so exceptions are also going to be defined as synchronous events that are going to be associated with the software requesting something from the hardware, something that the hardware can't perform. And so exception is going to be somewhat of like an error, and it can be based off of a legal addressing or a legal opcode, etc. It's basically going to trigger a warning that you're trying to do something that you're not privy to do. And so how can we break down the components that are associated with each type of exception, a trap, and an interrupt? And so we want to keep in mind that with regards to an exception, it is a synchronous event. The source is going to be internal, and it's not intended to be intentional. And so some specific examples associated with this could be overflows, divide by zero operations, illegal memory address access or calls. A trap is going to be represented as a synchronous event. The source is typically going to be internal, and it can be either can or can't be intentional. So it could be either one. And this could be based off of a system call, page fault, or some other instruction error. Then when we consider interrupts, we can consider interrupts to be asynchronous events caused by some type of external source that are intentional, and the external source could be resulted from an example such as an I/O device. It could be a mouse click or keyboard clicking as well. And so what is a good example of a trap? And so what would be an example of a trap? It could be, is it a keyboard input, B, a system call to open a file, C, an attempt to divide by zero, or D, an arithmetic overflow operation, E, a high-speed I/O request. And if you answer a system call to open a file, then that is a good example of a trap. And so when we're dealing with these these different discontinuities, let's consider how it would affect the execution path. And so we can consider that that these discontinuities could happen anywhere during our program or instruction execution. And so it could happen in the middle of the instruction execution, and oftentimes it can be unplanned, and it can be completely unrelated to the current activities that are being completed. Therefore, it's important that hardware have appropriate mechanisms in place in order to save the current state, store the program counter values and allow for control of the handler to handle the event in question. And so it's important to have appropriate mechanisms in place to analyze and evaluate the discontinuity. And so hardware needs to be capable to determine the address of the handler so that control can be transferred and that the currently executing program is able to handle it appropriately. So since you also want to ensure that hardware has appropriate mechanisms in place to handle the program counter implicitly. And so, and how exactly can we have these appropriate mechanisms in place? In order to do this, we introduce a new internal processor register. And this is going to be the exception trap number. So this can be the exception trap register is going to be internal to the processor, and it's going to allow for appropriate storing of information related to the exception or trap. And in this case, it's going to be a unique number that is going to be placed within the ETR. And so if we have, for example, a divide by zero exception, then our finite state machine will need to account for that, and we'll place it in the vector corresponding to this exception in the ETR. And so in order to accomplish this, we can also have a interrupt vector table. And so the interrupt vector table is going to represent a structure that is used for each discontinuity event. And so for each event, it's going to be given a unique number within the vector. And so for each index in the interrupt vector table, we're going to be able to represent each of the program discontinuities that need to be stored. So once the IVT is set up, we want to ensure that the processor is able to utilize the table during program execution in order to look up specific events and discontinuities that have occurred. And so some examples of these events could be if we have a handler code, we have for divide by zero exception, for overflow exceptions, system calls, page fault traps, as well as mouse interrupts and keyboard interrupts as well. So these are a couple of the discontinuities and events that can be stored in the interrupt vector table. And so some things that you want to keep in mind when dealing with program discontinuities is that, of course, they can happen at any time or any place during program or instruction execution. They can be unplanned for and forced by the hardware. So hardware needs to save the program counter since we are jumping into the handler. The address of the handler is going to be unknown, so therefore hardware must manufacture this address. And since hardware has to save the program counter, the handler has to discover where to return upon completion. And so what changes do we need in order to handle program discontinuities? We need to determine when should the processor handle an interrupt. We need to understand how does the processor know that there is an interrupt. How are we going to be able to save the return address? How do we manufacture the handler address? And how do we handle multiple cascaded interrupts? And how do we return from the interrupt? So these are some specific scenarios and events that we need to take into consideration and have appropriate mechanisms in place for the processor to handle interrupt events. And so we have our finite state machine where we have our microstates of fetch, decode, and execute. Where exactly would we need to handle an interrupt, and what modifications do we need to make to our finite state machine in order to accomplish this? So in order to accomplish this, we can make a modification to the finite state machine and introduce a new macro state that can handle appropriate interrupts. And so since the interrupt can be generated anytime during the execution of an instruction, we add this microstate in between the execute and fetch macro states. And so now the finite state machine will check at the point of completion of an instruction if there is going to be a pending interrupt. So in this case, if the interrupt is equal to Y, then the finite state machine will need to transition appropriately. If there is no interrupt pending, then we can continue on to the next instruction execution, and this would return to the fetch macro state. So how can we account for this within software? What exactly do we need to include? So we'll want to make sure that our handler is able to save the appropriate process registers. It'll need to execute the device code. It will need to restore processor registers. And we'll want to make sure that we're able to return to the original program. And so those are the basic mechanisms that we'll want to consider. But we also need to consider what happens when an interrupt handler takes an interrupt. And so how can we handle or anticipate this? Let's take a look and understand the problem that could occur. So let's consider that if we have a simple interrupt handler, and then there is another interrupt while we're servicing the current interrupt, then this could result in the program counter value being lost in the original program in our register K0 address. So this would make it impossible for us to return to the original address. So by the time that we get to the second interrupt handler, we've lost the original program. And so this can create a point of confusion in that we don't have appropriate mechanisms in place in order to handle each interrupt address. And so this means that we need to make an appropriate change. And so in order to do this, we'll need a modification in that we're going to ensure that we save our processor register, including our K address register. We need to execute the device code, and then we'll restore the processor register and making sure that we include our interrupt address register as well, and provide for a return. To our original program. So now that we've been able to save and restore the interrupt address register in the handler, we also need to consider if there is a second interrupt that hits before we're able to save that address. And so we need to consider how many instructions does it take to push a register onto the stack. And so if an interrupt were to happen here, what we'll do is we'll need to save that register first. And so that gets stored first. And it decrements our stack pointer to make sure that we store it. And so what is going to happen if we get an interrupt after we decrement? So we don't necessarily have a way to prevent an interrupt from happening between certain instructions. So in order to account for this, we're going to need to account for how machine instructions can be handled at a higher level. And so would it make sense for us to be able to turn off interrupts between machine instructions? In order to account for this, what we can do is we can create a new process register. That is one when interrupts are enabled. And for an interrupt to be recognized for the microcode to advance to the int macro state, and an interrupt must be asserted, and IE must be 1. So in the int microstate, we will turn off IE before fetching the first instruction in the handler. And so in order to accomplish this, we're going to need 2 more instructions, EI and DI, to respectively set IE to 1 and 0. And we'll use EI after pushing register K0 onto the stack. So next we will take a look at how we can handle cascading interrupts using our finite state machine.